was the first thing we did. And then we used integration to find area using horizontal rectangles. And then we looked at finding volume using disks, and we moved those disks along the horizontal. And we just looked at finding volume using washers, and we moved those, we integrated along a horizontal axis. Today's lesson, we are going to be looking at volumes again, but today we are going to be looking at disks and washers, but instead of moving them along the horizontal, we're going to move them along the vertical. And there are times where it makes more sense to be looking for volumes by taking disks or washers and integrating along a vertical axis. But before we do that, let's go and excuse me, do 3 examples where we are revolving. We're revolving an area, in this case the area that's bound by y equals x squared, and the line y equals 9 and the y-axis. So it's got 3 sides to it, if you will, this area that we have bound. And we're going to rotate it first around the x-axis. The integration for that, this is just a review of what we were doing in volumes 2. Right? So this is the pi, that constant goes out front of the integration symbol. We're integrating from 0 to the upper bound, which in this case is a value of 3, right? So we're going along the horizontal, starting at 0, out to 3, one washer at a time, each washer being dx wide. So we're going to go from 0 to 3. The washer that we're looking at has an outer radius of 9. Right, so let's just quickly draw in one of these washers. So it's got an outer radius of 9, and then its inner radius is defined right here. The upper edge of the inner radius is defined by the function y equals x squared. The lower part defined by the x-axis. So again, our integral outer radius is going to be 9 squared minus our inner radius. The inner radius is defined as x squared minus 0, and then we take that and square it, and this is all with respect to x. And then if we were actually wanted to find the numerical value here, we would simplify this pi 0, 3. This would be 81 minus x to the 4th. And then once this has been simplified here, then we'll find the integral. Right? So 2 more before we start looking at verticals. So if we are rotating around the line y equals -3 here, what's going to happen is our outer radius is going to get larger, our inner radius is going to get larger. Both are going to get larger by 3. So that's integral we're going to be looking for. Again, is going to go from 0 to 3, but this time the outer radius is going to be 9 plus 3, or 12 squared, minus the inner radius, which is going to be x squared plus 3 squared, and this is all with respect to x. Right? We are moving these disks along the horizontal. Right? So we start here at 0 with our first disk, and then we just find each little disk between 0 and 3, and we're adding them all up, which is what this integral is doing. Last one, we're going to look at the revolve this area around the line y equals 12, which is way up here. So let's do this. We're going to erase our old washer, and we'll draw the new washer here. So the outer radius of our new washer is going to be something like that. And the inner radius of our new washer is going to be defined as that. That's not a very good washer, is it? But you get the idea. So let's just move on to the integral. Again, same format. This is all pi r squared. The pi is going to come out into the front. We're integrating from 0 to 3. Now in this case, the outer radius is from 12 down to our function. Our function is y equals x squared. So we're looking for from here down to there. So this is going to be 12 minus x squared is the outer radius. That gets squared. Minus the inner radius, we're going from 12 down to 9. So that's going to be 3 squared. And this is all with respect to x. Right? Before we move on to example 1, notice we're doing each one of these washers along the horizontal. So the width of each one of these washers is dx. This integral is happening all in terms of x. Right? So here's an x right here. The function is defined we're using the x. We're integrating with respect to x. The lower bound is an x value. The upper bound is an x value. Right? So now moving on to example 1, we're now going to start looking at what happens when we rotate not around the x-axis, but around the y-axis. So we're going to take the same exact area here. We're going to rotate it around the y-axis. When we do that, let me just draw in what sort of that shape is going to look like. Right. Let me try again. Make this look a little better for us. That's slightly better. We're going to end up, in this case, when we're rotating around the y-axis, we end up with a disk. Now this disk has a thickness. So the thickness of this disk is dy now. And we're going to end up integrating from 0 all the way up to the top here, up to 9. Right? So we're going to end up with an integral to find this volume. We're going to have an integral. It's going to have the same format because we're doing, oops, that's off the screen, sorry. Try again. The volume we're looking for, it's going to have the same format as before. We're doing these disks. The volume of each disk is going to be pi r squared. So here's our pi. We'll put out here just to remind us, right, the width, dy. We're going to be integrating. Now we're integrating, we're rotating this around the y-axis. Lower bound is 0. The upper bound is up here at 9. So this is from 0 to 9. And now comes the fun part. We need to figure out what the radius of this is here. So we have to be very careful. This point that's right here is some x value. some y value. And the y value is defined by the function. The y value is x squared. So now when we're trying to figure out how far this radius is right here, this is actually pretty easy. The radius here is simply x, right? So this has a radius which is x. So we're going to take the radius and square it, which would just simply be, in this case, x. Right? So we're going from here, the x value back to 0, x minus 0 squared. But we are integrating with respect to y. So what we need to do before we square the radius and plug it in here into the integral is we got to take our equation, y equals x squared, and we want to write it in terms of x, or in other words, x is equal to the square root of y. And the radius is x. Another name for x is the square root of y. So whereas up here, when we were rotating around the x-axis, we were writing our y value in terms of x. Now, instead of writing our y value in terms of x and putting it into the integral, we're going to do it the other way around, and we're going to write our x value in terms of y. So we can think of this point here not as x comma x squared, but as the square root of y comma y. And now we can finish this integral over here. So the integral is going to be the square root of y, the quantity, squared. And then, actually, let's do this, because my dy got a little bit too far away. We'll move my dy over. There we go. And now, when we've rotated this around the y-axis, this actually is a pretty straightforward integral to do, so we'll just do this out before we finish up here. Right? Square root of y squared is simply going to be y, and we're integrating from 0 to 9, so this is going to be pi times 1/2 y squared, the antiderivative of y, from 0 to 9, which, when we do this out, 9 squared divided by 2 is 40.5 times pi. End of the example 0, 1.